The transition from Optimus 2.5 to Gen 3 is especially important because Tesla has described Gen 3 as its first Optimus design specifically intended for mass production. According to Tesla, Gen 3 will bring major upgrades over version 2.5, including a redesigned hand. The company has also said that preparations for its first production line are already underway, with supply chain readiness being developed alongside the factory itself. Tesla plans to begin production before the end of 2026, with an eventual target of producing up to 1 million robots per year. That is a completely different ambition from building a few hundred demonstration units. A production target of 1 million robots annually means Tesla is approaching Optimus as a product that must eventually be manufactured at something close to automotive scale. For comparison, Tesla produced about 1.65 million vehicles in 2025. A single Optimus factory, capable of producing 1 million robots per year, would therefore have a theoretical output approaching the scale of Tesla's entire current annual vehicle production. And Tesla's plans go even further. In its Q1 2026 update, the company said preparations for its first large-scale Optimus factory would begin shortly. The first-generation production line, designed for an annual capacity of 1 million robots, is planned to replace the Model S and Model X production lines at Fremont. At the same time, Tesla said it was preparing Gigafactory Texas for a second-generation Optimus production line with a long-term annual capacity target of 10 million robots. That 10 million unit figure changes the picture dramatically. If Tesla were eventually able to reach that level of production, it would be manufacturing more humanoid robots in a single year than the existing humanoid robotics industry has produced over many years combined. And this is exactly why Optimus should not be viewed simply as another Tesla product. Tesla appears to be trying to build the manufacturing infrastructure for an entirely new category of machine. The company has also established a formal milestone for the potential scale of this business. Tesla's 2025 proxy materials define 1 million bots delivered as at least 1 million AI-powered mobile robots manufactured by or for Tesla, including Optimus and future successors or enhanced versions. That definition is particularly interesting because it does not restrict the milestone to one specific generation of Optimus. Instead, Tesla is effectively treating the robot as an ongoing product platform. Gen 3 could eventually evolve into Gen 4, Gen 5, and future generations, while maintaining the same broader business model. That approach also fits with Elon Musk's much larger prediction about the company's future. Musk has said that he expects Optimus to account for the majority of Tesla's long-term value. That is an extraordinary claim, because it suggests he does not view Optimus as a small side business operating alongside Tesla's vehicle operations. Instead, he sees humanoid robotics as potentially one of the company's most important sources of long-term value. There is a reason Tesla believes it can pursue such an ambitious goal. Musk has explained that much of the technology Tesla has already developed for its vehicles can also be applied to humanoid robots. That includes batteries, power electronics, advanced motors, gearboxes, software, and AI computing systems. Tesla has made essentially the same argument when presenting Optimus as part of its broader artificial intelligence and robotics strategy. In other words, Tesla may be able to transfer years of accumulated automotive engineering experience directly into robotics. The batteries developed for electric vehicles can provide the robot with energy storage. Advanced motors can generate movement. Power electronics can control those motors, while gearboxes can transfer mechanical force efficiently. AI computers can handle perception and control, while Tesla's experience with high-volume manufacturing could potentially be applied to the robot's physical production. But there is another piece of the strategy that makes Optimus even more interesting. At Tesla's CVPR 2026 event, the company described its robotics research as involving foundation models for robotics, including large-scale multimodal models capable of controlling robots through an end-to-end system that connects visual input, or pixels, directly to physical actions. Tesla also highlighted work involving model architecture, data, training, evaluation, safety, and reliable deployment in the real world. That suggests the real Optimus strategy is much bigger than simply building a more advanced mechanical body. Tesla appears to be working toward an integrated robotics ecosystem that combines hardware, artificial intelligence models, training data, simulation, real-world feedback, and large-scale manufacturing. If Tesla can successfully connect all of these pieces, Optimus could become far more than a humanoid robot. It could represent Tesla's attempt to build an entirely new mass-market technology platform, one that combines the company's automotive manufacturing capabilities with its growing expertise in AI and robotics. This is where the progression from Gen 3 to Gen 4 and eventually Gen 5 becomes especially important. With each new generation, Tesla can potentially improve the robot's physical design, while the underlying AI system continues learning from an increasingly large fleet. The more robots Tesla deploys into the real world, the more situations they can encounter and potentially learn from. Every new environment, interaction, and unexpected situation can provide additional data. That information can then be used to train and improve future generations of the robot. So when Tesla talks about producing 1 million robots, followed by a production line capable of eventually manufacturing 10 million robots per year, those numbers should not be viewed simply as manufacturing targets. They point to a much larger strategy. Tesla appears to be trying to turn Optimus into a continuously evolving technology platform. Gen 3 could establish the foundation for mass production, while future generations improve the robot's hardware, software, and intelligence. At the same time, increasingly large factories could make those improvements available to millions of machines. That is why Gen 3 could be much more significant than simply being the next version of Optimus. It could represent the moment when Tesla moves beyond proving that it can build a humanoid robot and starts demonstrating that it can manufacture an entire population of them. Optimus Gen 3 and real-time 3D mapping. But there is another major question. How will Gen 3 actually understand a completely unfamiliar environment, such as a house? Imagine Optimus Gen 3 walking into a home it has never encountered before. There are no clearly defined factory lanes, no predetermined robot routes, and no guarantee that objects will remain where they were previously located. A chair might be moved into the middle of a room. A child's toy could be lying on the floor. A dog might be sleeping in a hallway. A person could suddenly walk directly in front of the robot. In an environment like this, Gen 3 cannot simply rely on a fixed map. Instead, it needs to continuously build and update an internal understanding of its surroundings, while simultaneously performing whatever task it has been assigned. Tesla already has an important technological foundation for this kind of problem. Its vision systems analyze camera images for things such as semantic segmentation, object detection, and depth estimation. Tesla also uses bird's-eye view networks that process video from multiple cameras to create a top-down representation of the environment, including road layouts, infrastructure, and three-dimensional objects. The scale of Tesla's existing AI infrastructure is also significant. Tesla says a full version of its self-driving neural network system involves 48 neural networks, requires roughly 70,000 GPU hours for training, and generates around 1,000 different predictions or tensors at each time step. For Optimus Gen 3, the important point is not that Tesla can simply take its full self-driving system and install it inside a humanoid robot. The more important advantage is that Tesla has already spent years developing AI systems designed to turn visual information into detailed representations of the physical world. Tesla describes its autonomy software as creating an internal representation of the surrounding environment and then planning trajectories within that representation. Those systems also learn from real-world driving scenarios collected from a fleet of millions of vehicles. Tesla has also directly indicated that it is applying its self-driving AI experience to Optimus. In its company filings, Tesla says it is using AI learnings from its self-driving technology in bots such as Optimus, while describing Optimus as a general-purpose autonomous humanoid robot. That matters because it suggests Optimus Gen 3 is not being developed as a completely separate project from Tesla's vehicle AI efforts. The broader expertise Tesla has developed in perception, planning, training, and AI inference could potentially contribute to the robot's ability to understand and navigate its surroundings. But there is a major difference between simply seeing a room and actually understanding what is happening inside it. For example, Gen 3 might detect a small object lying on the floor, but recognizing the object is only the first step. The robot needs to determine whether it is a child's toy, a pillow, a piece of clothing, a fragile object, or something that could create a safety hazard. The appropriate response depends entirely on the context. A child's toy might need to be picked up and moved. A glass object might need to be carefully avoided. A sleeping dog should obviously not be treated like an ordinary obstacle. This means the robot needs to combine visual perception with spatial reasoning, physical awareness, and an understanding of its current task. The challenge becomes even greater when something unexpected happens. Imagine Gen 3 carrying a glass from the kitchen to a table when a child suddenly runs across its path. The original route is no longer safe. The robot would need to detect the child, recognize that the person's position is changing, determine a safer path, adjust its movement and balance, keep the glass stable in its hand, and then continue toward its destination. All of that would need to happen in real time. That is the real challenge for a general-purpose humanoid robot. It is not enough for Gen 3 to simply recognize objects. It needs to understand the environment, anticipate changes, react safely, and make decisions while physically interacting with the real world. Tesla's autonomy research already focuses heavily on planning and decision-making in complex real-world situations where conditions are constantly changing and uncertainty is unavoidable. That is very similar to the challenge a humanoid robot faces once it leaves a controlled factory environment. This is why the real goal for Optimus Gen 3 is much bigger than simply giving the robot better cameras. The robot needs a continuous loop connecting perception, spatial understanding, prediction, planning, and physical action. It has to take what its senses see, build an understanding of the environment, decide what to do, execute the movement, observe what has changed, and then adjust its next decision. And that raises an even more important question. How quickly can Optimus actually perform useful work inside a home? The real test for Gen 3 will not be whether it can simply walk across a room. The bigger challenge is whether it can complete ordinary household tasks efficiently and reliably without needing constant human supervision. Tesla appears to be moving toward a robot that can operate continuously in an environment where conditions change from one moment to the next. It could potentially carry objects, clean, organize rooms, move between different areas of a house, respond to people, and adapt when something unexpected happens. One major factor in making that possible is improved reaction speed and movement control. Gen 3 is being developed to move more naturally, maintain its balance more effectively, and respond faster to changes in its surroundings. This becomes especially important when the robot is carrying an object while moving through a home. For example, if someone suddenly steps in front of the robot, Gen 3 may need to immediately slow down, stop, or change direction without completely abandoning the task it was performing. Faster reactions, better balance, improved locomotion, and the ability to adapt to unexpected environmental changes are therefore critical parts of making the robot genuinely useful. But the more interesting question is what Optimus could actually accomplish with those capabilities. Consider a kitchen. Instead of performing one isolated action, the robot could potentially move between the refrigerator, countertop, sink, and dining area while completing an entire sequence of related tasks. In a living room, it could navigate around furniture, recognize objects that have been left on the floor, move those objects to appropriate locations, and continue working even while people are walking around it. The key is that perception, movement, and decision-making must work together continuously. The robot cannot treat every action as a completely separate command. Tesla's training approach could make this even more powerful. Optimus can reportedly be trained for as much as 16 hours a day using a combination of demonstrations, video, simulation, and repeated physical practice. This gives Tesla the ability to teach the robot specific behaviors, and gradually improve how efficiently it performs them. A task that initially requires slow and careful movements could become much faster and smoother after thousands of repetitions. And this is where operating time becomes an important measure of success. A useful household robot does not need to perform one impressive demonstration that lasts 10 seconds. It needs to work for hours, repeat the same tasks many times, recover when something goes wrong, and continue operating without someone constantly stepping in to reset or guide it. Tesla's stated operating targets for Optimus are also aimed at this kind of practical use, with roughly 8 to 16 hours of operation depending on workload and battery configuration. Imagine a robot that spends the morning organizing a room, moving objects from one location to another, helping with household preparation, responding when someone asks it to do something, and eventually returning to its charging station when its battery becomes low. The real breakthrough would not be any single task. It would be the ability to connect many different tasks into one continuous workflow while constantly adapting to the environment around it. That is ultimately what Gen 3 needs to demonstrate. Speed is not simply about how quickly Optimus can move its legs or arms. True speed means how quickly the entire system can perceive a situation, understand what is happening, decide what to do, perform the action, respond to unexpected events, recover from mistakes, and move on to the next task. If Tesla can make that entire cycle reliable, Gen 3 could represent an important turning point for Optimus. Instead of looking like a machine performing carefully controlled demonstrations, it could begin to look more like a general-purpose worker capable of completing an entire shift in a human environment.